So, first of all, I'd like to introduce myself. I'm Arsentiy Primushko, and I'm a PhD student in Puha Institute for Modeling in Energy Engineering. And um, thanks for organizers for the conference. Here, I'd like to briefly introduce the main thoughts from our research about representation and synchronization of states of distributed electrical grid systems based on conflict-free replicated data types. Later, I will call it CRDT simply. So for now, our modern electrical grid development is driven by majorly is driven by integration of renewable energy sources. It will be a big deal for Ukraine as well in the future. The other topics cover distributed management with decentralized systems, digitalization of monitoring, analysis, management, and fault tolerance and resilience in dynamic environment. Um, so in distributed grids, we have several challenges. Uh, the first and the biggest one is synchronization of distributed network states, because we need to operate on these states and to perform some management processes. So then we have maintaining a functional and structural consistency. In scope of this research, we mainly focus on functional consistency rather than structural. And the third point is critical infrastructure resilience and stability. So it's very critical for distributed electrical grids. Um, so our main focus of this research is to evaluate CRDT's potential in high load and real-time electrical grid environments. For this goal, we developed a separate um, uh, framework for modeling distributed electrical grid systems, and we will cover it later. Yeah, so we have several CRDT-based approaches in distributed system in general. So, like there is several consistency models. It's all about CRDTs. We have strong consistency, and in general, we have yeah, strong consistency. Uh, so and eventual consistency. Yeah. So we have two types of consistencies. It's like strong and eventually. And for this, in this current research, we rely on eventual consistency uh, because the actual model of the CRDT, which ensures consistency in distributed environments and allows concurrent operations with deterministic convergent final states by its nature, it allows us to operate within eventual consistency paradigm. Um, so for power grid modeling, we use a separate framework, developed framework, as I said, by us. It allows us to operate with power grid units using actor-based model. So basically, this model allows you to mimic any kind of power plant, like gas stations or charcoal units, etc. And this framework allows to uh, model a distributed network with uh, corresponding signals, messaging, and monitoring as well. So um, uh, each for our purposes, each power unit have different CRDT states. like we have a unique identifier, we have nominal and actual power, we have borrowed and returned electricity sets, and we operate within a simple state update formula, which which is based on formal definitions of CRDT. Um, so for this, within current work, we make experimental setup, which includes 100 nodes in some state. So we have several states for our power units. Each state simply indicate uh, where and why the unit should borrow or return some electricity to the customers or some other units. And uh, we modeled a simple framework and scenarios as well to model this turbulence. And uh, we mm, monitor the system transitions between the actual power unit nodes to verify how the messages described via CRDT is distributed using such systems. Um, so yeah, here we can see experimental results. So LDK here is latency degradation coefficient. We model the situation where the power grid units can be divided into several regions and be far from each other, or close to or close to each other. So this allows us to model some power losses, some network communication issues, etc. So at the left, you can see how message distribution within electrical grid with corresponding LDK works. And at the right, we can see results for network state synchronization with different LDKs. Uh, so yeah, and within this actual work, we found several interesting we had several interesting observations. So it was found that increasing distancing between nodes with latency degradation can cause turbulences and making the system more complex to manage in various forms. Therefore, we can also observe that each system has its own effective, let's say, that coefficients for message distribution and state representation. Uh, and therefore, we propose uh, to optimize it in some way. We will cover it in future research. Uh, we want to divide the cluster of some nodes into smaller subclusters. And naturally, such a division would require a specific topology and a specialized inter-cluster communication protocol to maintain connectivity within larger network groupings. Uh, Additionally, it is worth noting that under efficient coefficients, the system responded smoothly and predictably. So in general, we observed that the system behaved predictably and consistency was maintained after the disturbance. Uh, so based on the facts within our experiments, we conclude that this technology is very perspective within modeling of such systems, particularly within power grid, electrical power grid systems. So yeah, that is basically the end. So I thanks for the listening and will be glad to reply to your questions. Thank you.
Mhm. Thank you for your presentation, Arsenki. Colleagues, do you have any questions?
I have one question.
Yes, please.
Arseny, what kind of data the state of a grid consists of? Why do we care about synchronizing the state of parts of electrical systems?
Yeah, so thanks for your question. It's a good question. So in general, newest electrical grids developed in such way that we integrate a lot of IoT systems, a lot of management tools, and so on. So it's a very high level and distributed high load systems which require a simple and predictable way to manage them. And the way we want to manage them is a way where all nodes, at least for us, all nodes are synchronized or in a similar, not convergent states. So we can simply make good predictions, scale this data, and manage them for efficient usages. That is why.
Thank you.
One more questions, please. I have a question to you. Talking about the network states synchronization, what indicators you must take into account in order to manage the synchronization processes?
Yeah, so in current work, we relies on state-based replicated data types, delta-based, I'm sorry. And ask, replying to your question, we rely to indicate a proper deltas within power grids. So these deltas spread among cluster using CRDT technology, and we indicate a proper state changes on each power unit, and therefore we conclude that the actual state of the system is consistent or inconsistent.
And when we talk about the synchronization, you mean synchronization data in information network.
Yes,
And
yes, yes.
how about the electricity network of distributed systems?
Yes, so in scope of this work, we mainly rely on the information network. So as I said at the beginning, we uh, left the low-level implementation, particularly uh, power grid synchronization, electrical in electrical way,
Mm.
and perform investigation in information communication domain.
Mhm. Mm. Thank you. Any questions, please?
Yeah, can I?
Please.
Uh, in your conclusion, you talk about the scalability. So, can you discuss the scalability of your approach in large-scale grid networks?
Yeah, sure. Thanks for your question. So, in scope of this research, we propose to, uh, as I said, divide bigger clusters as on a smaller one using some topologies. This is our potential solution for better scalability in scope of using CRDTs. But in general, CRDTs is a very flexible solution because it has different message distribution techniques. So for the current work, we used delta replication technique, which is not heavy by itself, and it is very compliant with different protocols and within network communication. So we have experiments where we model big units, big power grid systems within hundreds of units, thousands, and even bigger numbers. So they all behave in the same way. So this technology, if we are talking about scalability, is very predictable and, from my opinion, is very reliable.
Okay, thank you.
One more question? No one. Thank you, Arsenty, for your presentation.